Said, I work in the physics department as part of the kind of space, plasma, climate community or grouping of people, but ultimately my research area is clouds. And in particular, what I want to understand, or what our kind of work looks at, is how humans change the properties of clouds and ultimately what that means for our climate. So first, I've got a question. I couldn't set this up as a Zoom poll, so you'll have to kind of think about the answer in your head. But how cloudy is the Earth? Is it 5%? This is what you'd suggest if you watch Battlestar Galactica. Is it 20%? It's Star Trek 4, the Voyage Home, the one with the whales. Is it 40%, which is what you might get if you look at the Natural Earth data set, which is often used for kind of making fake pictures of the Earth? Or is it 60% covered in cloud, which is what you might get if you took your kind of picture from the film Armageddon? So actually, the thing that might be kind of surprising is it's 60% or even a little bit over. If we look at a satellite image of the Earth, or in this case, one of the images from the Artemis mission from earlier this month, about 60% of the Earth is covered by cloud at any one time. I quite like this one because it's a picture of the Earth at night, and normally, obviously, you can't see clouds at night, but it's very clear here with the moonlight illuminating the clouds. Now, the clouds themselves vary quite a lot across the Earth, and the amount of clouds you get in different regions really kind of varies quite significantly. But overall, it's about 2/3 of the Earth that's covered by cloud. Now, what that means is clouds and the variations of cloud then have a big impact on, there we go, that's going to work, on the energy received and emitted by the Earth. So the Earth receives energy from the sun, but clouds are white and reflective, and so light that hits clouds will get reflected back into space and not absorbed by the Earth. So they have a cooling effect on the Earth that way. But they also trap infrared radiation. So on the right here, you're effectively seeing the temperature of the Earth. So warmer things emit more energy as infrared, a little bit like when you can feel the kind of warmth of a fire. And so where it's red, the Earth is emitting more energy. And you can see, for example, the Sahara in the middle here kind of heating up during the day and cooling down at night. But the clouds here are often showing up as blue. They're trapping energy in the Earth system because they're cold. And so if you change the amount of cloud, you can change the amount of energy the Earth absorbs and emits. And so they help modulate the temperature of the Earth. Now, they're not just important for the energy balance, the setting the temperature of the Earth. They're also important for rain. Right? Our rain comes from clouds. This here is a satellite product showing roughly where we're expecting the clouds to be raining from this image here. And so obviously, if we want to understand where rain falls on the Earth, really we want to have a good picture of how clouds work. And ultimately also, almost every planet in the solar system has clouds on it as well. Right? So Mercury doesn't have clouds, but it doesn't really have an atmosphere, so I figure that's kind of fair. But every other planet in the solar system has clouds, and so if we want to understand those atmospheres, we want to understand how clouds work. Now, one of the things that we focus on in my research group is how clouds respond to changes in aerosols. So these are little particles that come from a variety of different sources. So they can come from natural sources, so things like desert dust or sea salt. These are tiny particles, nanometers to a micron in size, so kind of smaller than the width of a human hair. But when you have enough of them, you can see them from space. So in the top picture here, we've got this kind of brown blob coming off the Sahara Desert. And this is dust being blown off the desert and over the ocean. And so that's where the satellite can see it. But actually, if you live in a city, potentially like London, you see these aerosols day to day as well. Right, so if you look out across London on a clear day, so this is a picture taken from Imperial, you can see out to the Docklands, for example. There's Big Ben and the Shard in the middle. But if you look out on a particularly polluted day, it might look something more like this, right, where you've got this kind of haze, kind of preventing you from seeing. I mean, you can hardly see the Docklands at all. Maybe you can just about pick out the kind of Canary Wharf Tower here. But this haze is made up of these aerosol particles, these little particles which are scattering light. Now, many of these particles are also really good at forming cloud droplets. So if you think about a cloud and it's composed of lots of little droplets of water, almost every droplet of water in that cloud will be formed on one of these aerosol particles. So if we're thinking about kind of a schematic or an imaginary cloud at this point, it starts when we get some aerosol and it's sitting in kind of rising air, it gets drawn into that cloud. And the first thing that happens is some of those aerosol particles become cloud droplets. We say they activate and they form cloud droplets. Not all of them, but kind of a fairly high proportion become cloud droplets. And as that air rises up through the cloud, those droplets grow. So you're getting more and more water molecules getting stuck onto those droplets, and they're getting larger and larger. They're still small at this point. They might be 10 microns across, so approaching the width of a hair now. But you have quite a lot of them. So in a cubic centimetre of cloud, you might have maybe a couple of hundred cloud droplets. Now, these droplets grow and they get larger and larger. And eventually, at some point, they can get large enough that when they start hitting each other, they start sticking together. So really small cloud droplets, they kind of bounce off each other. But when they reach about 15 to 20 microns now, so heading up to a bit larger than the width of a hair, when they hit each other, they stick together. And once that happens, they start growing very quickly. You're no longer having to stick individual water molecules onto the edge. Your droplets are large enough that they can grow really quickly by collecting up other droplets. And eventually at that point then, you might expect your cloud starts to rain. Now, one of the questions we have is, what if you add extra aerosol to this cloud? So these aerosols that are formed maybe from burning fossil fuels, for example, if you have more of these aerosol particles and they get drawn into a cloud, you might then expect to have more cloud droplets. But those droplets will on average then be a bit smaller because you're sharing the same amount of water out across more droplets. And if you've got smaller droplets, those droplets are going to be less likely to stick together. And so your cloud then might not rain as much anymore. Now, we actually have really good evidence that this kind of thing happens in the real atmosphere from point sources of pollution. And a really good one here is ships. So ships sail in an otherwise relatively clean ocean, but they burn a really dirty fuel. And so they produce lots of aerosol particles. So if this video works, let's see, we can see here in this video, this is a video taken by a weather satellite. And so it's constantly watching the development of clouds. And you can see these kind of linear trails here in the cloud. And these trails are where ships have sailed. And so as they sail underneath the cloud, they add more aerosol to that cloud. They make the droplets smaller. Cloud may be less likely to rain. And at that point, then it modifies how the cloud evolves over time. Right? So if that cloud is less likely to rain, maybe it gets more water. Maybe it lives longer and so it spreads out more and so you get more cloud around as well. We get some hints about what might happen from these ships, but overall what we care about is how it impacts the climate. So, now ultimately we know that aerosols are making clouds brighter. Right? A polluted cloud has lots of small droplets in it, and that cloud might live longer. And so if you've got these clouds that are potentially longer lived and with smaller droplets in that makes the cloud a bit brighter, that means that cloud reflects more light back into space, and so it cools the Earth. We try and quantify this by a property called radiative forcing, which is essentially telling us how much extra energy the Earth receives or emits per unit area. And so greenhouse gases have a positive radiative forcing. They warm the Earth, somewhere around 3 watts or so per meter squared. Aerosols cool the Earth, primarily by changing clouds, at about 1 watt or so per meter squared. So they offset some of the warming from greenhouse gases. But the exact amount they offset the warming is uncertain, right? So this estimate here comes from about 20 years ago at this point. If we update that to one that's more about kind of 6 or 7 years ago, the cooling is a bit larger. But you can see the error bars here are still really large, right? Much larger than the ones we have for greenhouse gases. And so ultimately, our uncertainty in how clouds respond to these particles means we don't quite know how hard we're pushing the Earth to change through climate change. And this means that we actually have quite a lot of uncertainty about how the Earth will change in the future. So these two kind of realizations or simple climate models here, one of them has a very strong aerosol cooling effect. So the clouds are very sensitive to the additional aerosol, the additional particles you add. And the blue one here has no cooling effect at all. And you can see here, actually, throughout the 20th century, they're pretty close together. right? You can't easily tell them apart based on their behavior in the 20th century. But as you move into the 21st century and your greenhouse gas emissions continue to increase, you have a big difference in how much warming there is. So we really want to understand how the clouds have changed in the past if we want to be able to understand how the Earth is going to change in the future. There we go. And primarily this uncertainty here is coming from this change in clouds. Now, part of the issue with clouds is that they operate across a wide range of scales. So the cloud droplets themselves are very small, as I say, about the width of a human hair, and you have a lot of them within each little kind of parcel of cloud. The clouds themselves can be much larger, right? So this picture from the International Space Station has some of these big storms here over Africa that can be hundreds of kilometers across. But if you're going to simulate the Earth in a climate model, you can't simulate all of these little droplets. There are too many of them. You need to chop the Earth up into chunks, and those chunks can be quite large. So a typical climate model might chop the Earth up into chunks that are maybe 100 kilometers across, which is something like this. And you can see here that the clouds are much smaller than that grid box, right? So within that grid box, you can't simulate individual clouds. You need an equation that tells you how those clouds work, right? We're trying to work out what is the equation for a cloud. And it's tricky because that's not even really a well-defined question. Like, what do you mean? Like, what should that equation be doing? So one of the things people have tried to do in recent years is to make our models higher resolution, right? So instead of having a chunk that's 100 kilometers across, you could move to chunks that are maybe 1 kilometer across. And at that point, then our models are becoming increasingly good. They look more and more like reality. So for these 9 images here, one of these is a real satellite image, and the other 8 here are now model simulations of the same day. There are ways to tell them apart. It turns out that students are actually really good at doing this, spot the difference. So the real one here is the one in the middle. And one of the ways you can tell is you can see the ocean here is slightly kind of shiny in the middle, and you don't get that in the other ones. That's the reflection of the sun on the ocean. And so when they made these kind of fake satellite images, they didn't simulate that part. But ultimately, these things are really close together, right? They're looking pretty reasonable, but we're still not simulating those individual droplets, right? And ultimately, we can't. Like, even if computers continue to grow and become faster and faster following Moore's law, so they kind of double in capacity every year or two, it's going to take us close to 100 years to have a computer that's big enough and fast enough to simulate every droplet on Earth. Even today, the most powerful computers can't simulate every droplet in a cloud. So what that means is we can kind of see kind of large-scale changes, and we know how they work on a small scale. We can go and measure how cloud droplets behave in a lab. But when you put lots of droplets together, what do they do? How do the different processes interact, and how do they create that large-scale change? In some ways, this is almost opposite to a lot of things we do in physics. If you think about particle physics, we kind of know how the Earth behaves on a large scale, or the world behaves on a large scale, but we want to work out the individual rules that help govern that. In this case, we have a pretty good idea what the small scale rules are, but we don't quite know what happens when you add all those small scale rules together. So obviously, as scientists, what we'd like to do is we'd like to go and do an experiment, right? We'd like to see, well, what happens if you add more aerosol to these clouds? Now, in general, people don't like you messing with their weather for very good reasons. But there are some cases where we can see these experiments happening, even though we don't have control over them. We want to see what would happen. And we've already actually seen an example of that, right? So ships are an example of our kind of us experimenting on clouds in the wild. This here is a satellite image, but obviously a false color image of the Earth. For those of you who recognize California, that kind of sits along here, but it's sideways. So north is off to the right. And you can just about see kind of Monterey Bay here. Los Angeles is down here. San Francisco is up here. Now, what this is, it's showing us this kind of false color image is set up to show us lots of different things about clouds. But the thing we'll focus on here is the difference between the pink and the green parts of the cloud. So if you look at clouds in infrared, you can see this, you can see the size of the droplets in the cloud. And so pink typically means in this case that the droplets are larger, and the greens mean that the droplets are smaller. And so these lines here are where you've got kind of trails of smaller droplets, and that's where the ships have been. Right? The ship's adding more aerosol to the cloud, and you're sharing the same amount of water out across more droplets, and so those droplets are on average smaller. Now, what we can do is we can take this satellite image and we can match it to data about the ships. Right? So we move on from saying there's a cloud that was changed by adding aerosol to it to saying that ship changed that cloud in this way. We can kind of zoom in a little bit here. So these black dots are the locations of the ship. The red dots are the locations in the past. And this thin black line here is our kind of estimated locations for the ship emissions. And you can see in this case here, this green trail here was definitely caused by this ship. There was nothing else around that could have generated it. And so we've now moved to this case where we know that there was a particular ship that caused this change in the cloud. And if we know what kind of ship it was, we can make a pretty good estimate as how much aerosol it was generating. And so now we say we've got an image of a cloud, we know we've added this much extra particulate, and we can see the response of the cloud. Right? So we're very close to having that experiment we would like. We can't make the ships go exactly where we want, but there are a lot of ships, right? And so we can map out where ships modify cloud across the globe. And that gives us a way of experimenting on clouds across the globe, right? Each of these little ships here is running an experiment on the cloud above it, assuming there is some cloud there. And you can see some of them here are forming trails, these so-called ship tracks. Now, there are a lot of ships, and so we don't want to kind of sit there by hand mapping all of these out. But luckily, computers are really good at this, right? If you give it a few examples and say, find me things that look like this, you can get it to look at all of the ships across the global ocean. And it comes back with things a bit like this, right? So in the middle of each of these images here, there was a ship, and we would expect the trail, if it formed, to be kind of down from the center towards the bottom. And so these ones at the top, the computer said, well, there's no trail there. But the ones at the bottom here, it started to identify trails. In this case here, this one's actually sitting behind another cloud. But we can do this across the globe, and then we can start to map the locations where clouds are sensitive to ships, which ultimately then is giving us some information about where clouds are sensitive to these aerosol particulates. And that's what we can start to do here, right? So this here is an image of where you see ship tracks. So where do you see these trails in the cloud across the globe? And you see lots in the Northern Hemisphere. Right? But that's not exactly surprising. We know there are lots of ships in the Northern Hemisphere. The majority of the world's population lives in the Northern Hemisphere. If you're shipping stuff across the Pacific, for example, from China to the United States, you wouldn't go via the Southern Hemisphere. Right? And so we would expect there to be lots of ship tracks in the Northern Hemisphere anyway. But what we can do instead is we can say, well, okay, given I know there was a ship there, how likely is it to have formed a track? And then we get plots that look more like this. Right? So where it's red, it means that a ship is more likely to have impacted a cloud. And now we can see actually that while the North Pacific, if you have a ship, it's quite likely to have changed the clouds in the Southern Hemisphere are really sensitive to aerosol. Right? So if you add this particulate to clouds, you can generate a big change. And this is something we didn't really know before. We weren't able to see that before we could effectively go and run these experiments on these clouds. Now, the other thing we can do is we can use our ships to test how well our models work. So this here at the top now is simulated ships running through a simulation with the Met Office weather model. Right, so these trails here are, so we're looking at the number of droplets in the cloud now, and at the top of each of these trails is a ship. And you can see as these kind of imaginary ships are moving through the weather model, they're generating these trails, and we can compare it to a specific case, right? So in this case here, we haven't simulated all of the ships, but we've simulated some of these ones here, and you can roughly match up these trails here with the ones we see in the model. Now, the model is missing some things. There's a big blob here of clouds with very high droplet number concentration. So this is essentially pollution from the land that the model didn't include. And similarly, there's a blob out here of the open ocean. But for the cases where we think that it got the background cloud right, it's got the sensitivity to aerosols about right as well, which is nice. Now, actually, I think one of the really exciting things you can do about this is instead of using it to test the clouds, you can say, if I know enough about the clouds, I can measure something about what the ships are doing. And that's what we look at here. So now what we do is we say, well, okay, I can see lots of these ship tracks. How does it change over time? Like, do I get more of them, less of them? Where are they? This here now is the western coast of the United States and Canada. These black dots here are some of the major container ports. And this red line here is the edge of the US and Canadian exclusive economic zone. So if we start by looking at 2003, where we see red here, that means we've got lots of tracks. And in 2003, we see lots of tracks. They're kind of in between Los Angeles and San Francisco, where we know there are lots of ships. So it's not exactly unexpected, right? We're seeing lots of tracks, lots of trails in the cloud where we see lots of ships. In 2014, it's quite similar. We still have this big blob near to the coast where we've got lots of tracks and where we expect lots of ships. We see this kind of line here now where we're also expecting lots of tracks. This is the route between Panama and East Asia and China and Japan. Right, so as we've shifted forward 10 years, that kind of trans-Pacific trade route has become a lot kind of busier. The ships using it have become larger. They impact the clouds more often, and we can see that in satellite data. When we move to 2015, something strange starts to happen. We still see this trail here between Panama and East Asia, right? So the ships are still modifying the cloud, but next to the coast, the trails have almost completely disappeared. And that stays the case into 2016 as well, right? The Trans-Pacific route is still there, but the ships near the coast are no longer generating trails. Right? It's not the ships have disappeared. They're definitely still going to Los Angeles, San Francisco, Vancouver, but they're no longer generating trails in the cloud. And this effect is actually so large, you can see it in individual cases. Right? So this image at the top here is from 2003. Here's Monterey again, San Francisco up here. And you can see these trails in the cloud. Right? This is the edge of the US economic zone. In 2015, you can see trails outside, further away from the coast, but not in this region next to the coast anymore. We know the cloud is still sensitive, though. As you see this big blob here, this is the pollution from the city of San Francisco, right? And San Francisco is still modifying the cloud, right? It's generating these particles that are changing the cloud, but we can't see the changes in close to the coast anymore. And it turns out what happened in 2015 was the US and Canadian governments implemented a regulation that made the ships have to burn much cleaner fuel, right? So in these red regions in 2015, ships were restricted from burning very dirty fuel to burning kind of less dirty fuel that produced fewer of these particulates. Right? So this is this kind of black line here. This ECA is the emission control area. And in 2015, they went from being allowed to burn fuel that had 1% sulfur down to effectively zero, only 0.1%. And doing that made these trails disappear. Right? So when the ships are no longer burning kind of high sulfur fuel, they don't produce these aerosols, these particulates, and they don't modify the cloud anymore. And we can see that happening with satellites because we know enough about how the clouds work. We also see a similar thing around Europe. Europe's a little bit harder, but you can see in 2003 we have kind of a reasonable number of tracks here in the North Sea and in the English Channel. And in 2015, they've largely disappeared. These kind of bits here are mostly oil rigs, actually, that generate these trails in the cloud. I'll skip through that one because we can also come on to kind of this question of what happens if you do this on purpose? right? So we've thought about here what happened if you removed these ship tracks or removed kind of aerosol pollution from shipping exhaust, right? And that happened in 2015. In 2020, there was a much larger change to ship fuel, right? So ships on the open ocean were previously allowed to burn very high sulfur fuel, and that was restricted to actually relatively clean fuel in 2020. And this produced an impact on the climate, right? So these ships are no longer producing these aerosol particulates. Particularly, they're no longer producing them in very clean regions in the open ocean where the clouds are very sensitive to particulates. And so we think that that changed the clouds, right? So these aerosol particulates make the clouds brighter. If you have fewer aerosol particulates, the clouds become dimmer. And so if you clean up shipping emissions, you get a bit of an extra warming. So this here is a climate model simulation of the kind of 19th, 20th, and into the 21st century, with this change in shipping emissions implemented in 2020. Right, so the blue line here was the kind of no change in ship fuel, and the orange line here is cleaner ship fuel as implemented in 2020. And these lines are very close together, I'll admit. If you zoom into 2020, the change becomes a bit clearer, right? So here in 2020, we can see the kind of change, and this change now is temperatures relative to 2020. And we see in the case with cleaner ship emissions, you've got kind of a warmer Earth going into the future. If we just look at that difference, you see by 2030, we might expect the Earth to be about 0.05 degrees warmer than it would have otherwise been due to this cleanup of ship emissions. So this then raises the question, well, if taking out sulfur from fuel heats the Earth up, and we've got a problem with climate change, should we put the sulfur back in? And maybe even put more back in to cool the Earth back down, right? Can we or should we do this on purpose? Should we put this pollutant back to keep the Earth cooler? So again, this is kind of going right back to that image at the start, right? Clouds reflect sunlight to keep the Earth cool, but they also trap infrared to keep the Earth warm. And so what we're suggesting here is maybe we could make clouds more reflective and keep the Earth cool. The reason this might work is that ultimately the Earth is in a kind of balance, right? There's energy it receives from the sun. So this big blue line here is the energy the Earth receives from the sun. Some of that gets reflected back to space. The rest of it gets absorbed. And the Earth then emits infrared radiation to cool down. And ultimately, if these things are balanced, so the energy in from the incoming sunlight is balanced by the sum of the reflected sunlight and the outgoing infrared, the Earth stays at a constant temperature. What's happened recently with increases in greenhouse gases is that we've reduced the amount of outgoing infrared radiation. Okay, that arrow gets a little bit smaller, but ultimately now there is more energy coming in from the sun than is leaving the Earth system. And so the Earth is heating up, right? And this is what's giving us climate change. The suggestion here would be, well, maybe we could increase the amount of reflected sunlight, right, and bring these things back into balance again. Okay, so our incoming and outgoing energy balance again, and that would stop the Earth's temperature changing. Right? And this is what's known as solar radiation management, occasionally SRM, right? And so this would be our kind of SRM world, where we've changed the clouds to keep the Earth cooler. Now, ultimately, we kind of know that we could change clouds because it has happened in the past, but what would the impact be? Right? What would an SRM world look like? Now, obviously, we don't know because we haven't had that world in the past. We haven't seen that world in the future. It's in our future potentially, but we have some idea about what it could mean. And so the first one is that this cooling from these changes in clouds is going to vary by region. Right. This image on the left here shows us the temperature fingerprint of greenhouse gases. So if you raise the Earth's temperature with greenhouse gases, where do you see that warming? And that warming, it's kind of fairly even across the globe, but with generally kind of much larger warming in the Arctic, a bit more in the Antarctic, and generally it's kind of an increase in warming over land compared to the ocean. But the cooling we get from aerosols, at least in the past, has been concentrated in the Northern Hemisphere because that's where we've released them. And these aerosol particles, they don't travel across the whole globe in general, right? They produce a cooling near where you've released them. So any cooling we would generate would be highly regional. It wouldn't be a global effect unless we were somehow able to produce these kind of aerosols across the globe. The second important thing is that we know that this cooling wouldn't be easily targetable. Right? So we know here that the Arctic is warming more quickly from climate change. So maybe we could say, okay, we could try and modify the clouds in the Arctic to target the cooling in the Arctic, where the warming is largest. And climate models suggest, well, if you tried that, you might be able to produce a recovery in the Arctic sea ice, right? So this plot on the left here is a not quite business as usual, but kind of what Arctic summer sea ice could look like kind of 30 years or so in the future. And this one on the right is in a case where we've modified the clouds to cool the Arctic. But this leads to a significant drying in Africa. It shifts the rain belt in Africa further south and away from kind of regions of sub-Saharan Africa, in some cases out over the ocean, right? So these brown regions here would experience quite significant drought if you did this Arctic cooling. So there's a definite downside there, right? You can't target the cooling just at the regions you want. Right? The cooling and changes across the Earth happen in other regions as well. Ultimately, it's part of this is because it's not really addressing the cause; it's only addressing the symptoms. Right? So remember we said that the warming across the globe happens broadly globally for greenhouse gases, but with stronger warming in the poles. Cooling from changing clouds is going to be much stronger in the tropics because that's where you have large amounts of sunlight, and so you can reflect more of it. So if we try and get the Earth's average temperature back down to, say, pre-industrial, in this case here, you can see that a lot of the tropics would be cooler than it was previously, while the poles might be warmer than they were previously. And if we look at what that means for rainfall, in this simulated case where we've cooled the Earth by changing clouds, we get a big reduction in the amount of rain. And again, the reason for this is that changing clouds changes how much energy is reflected by the Earth, but changing CO2 changes how much infrared energy the Earth emits. They're working on different bits of the Earth system, and so they're not directly, they don't directly cancel each other. And ultimately, this is because we would be moving the Earth to a third state, one we haven't seen before. Right, so we have a pre-industrial and we've heated the Earth up by increasing greenhouse gases. Changing clouds to cool the Earth down doesn't move us back to the pre-industrial. It moves the Earth to a new place, one that we haven't seen before. Right? And we think that will probably give us decreases in rainfall. We don't know exactly where, but a lot of climate models suggest that decreases in rainfall might occur over the Amazon. So this is a climate model simulation here. And if you do that, this climate model simulation suggested that you would have large decreases in the amount of vegetation in the Amazon as well, right? So potentially generating a large dieback in the Amazon. And at that point then, is this solution or is this cure worse than the original problem? I don't think the answer is necessarily clear, right? Clearly in this case, this climate model suggests that the potential solution is not something I think we would want. But the impacts of climate change are also severe and already here. And so at the very least, it's something we need to know kind of how this, or kind of what the least damaging way of doing this might be. Ultimately, as scientists, the decision of whether to do it or not is not going to be up to us. So we need to have some idea, if we're asked, how this could be done in the least damaging way. So ultimately then, we know that humans are warming the climate, and this aerosol impact on cloud offsets some of the warming. Right? Aerosols change clouds to cool the climate, but this leads to large uncertainties in the future change, partly because we don't know how much the Earth has changed or how much we've changed clouds in the past. One way we are learning more about this is by using ships to effectively run experiments on clouds. Right? These ships are sailing along, they're not under our control, but they release these particulates into the cloud. And they show us how clouds change at a small scale. That helps us understand how clouds change at a larger or a climate scale as well. And quite nicely, if we know something about how clouds work, we can also use that to track where pollution or kind of where ships are generating this particulate pollution, potentially even to track the kind of fuel they're using as well. And finally, changing clouds on purpose might be able to offset some of the impacts of climate change, but ultimately it's only treating the symptoms. It doesn't treat the cause. And there are potentially quite severe side effects from doing this. So if this is something that's to be considered in the future, we really need to understand what those side effects are to understand whether this is something we'd ever really want to consider. Okay, that's all I had to say for now, but I'm very happy to take any questions, ideally about clouds, but I guess I can do other questions as well.
Yeah, thank you very, very much, Ed. I certainly am quite enthusiastic about learning about this sort of thing, but I learned quite a lot from what you had to say and the way you put this together. I think it was a magnificent presentation, and one that should make us all think, because we're all concerned about climate change, and so we want to manage the planet better. But what you're telling me, and probably the rest of the audience, is even if you've got all the governments in the world wanting to do the right thing, it's very hard to see quite what the right thing is because of the unintended consequences of some of the obvious things you would want to start on. Am I being unduly depressive about this, or?
I hate kind of SRM, frankly, like geoengineering. Partly because I kind of got into this because I quite like clouds. I want to understand more about how the Earth works. I want to kind of understand about climate change, but also I just think they look quite nice, right? There's so much kind of complicated stuff going on, right? From the smaller scales up to the large scales. The thing I tell people on undergraduate open days is the thing I really love about them is they draw together so many different bits of physics. Like often when you end up going into a PhD, you end up kind of specializing on some part of undergraduate physics. And the great thing about the atmosphere is that actually I feel I use still even a lot of my undergraduate physics day to day. Right. Obviously, there's kind of fluid dynamics there, but there's also kind of optics and electromagnetism if you're thinking about how light interacts with things. You even get to do kind of bits of chemistry, although I'm a little bit terrible at that. And even biology. There are certain kinds of bacteria that are really great at kind of forming ice in clouds. And the thing I kind of find about SRM is that, and this kind of like purposeful change in the climate, is that ultimately there are definitely parts of it that are, I guess, more of interest to kind of military and defense. And if that's what needs to be done, that's fine. But I feel kind of annoyed about it because I quite like clouds for the kind of intellectual part of it rather than necessarily being involved in the defense part of it. In terms of whether we should do it, I think it's probably, ultimately the great thing about climate change, we know what the solution is. Right. If you think back to kind of the early days of COVID, like there was a question as to whether we could even produce a vaccine against COVID. But with climate change, we know what the solution is, and broadly we know how to get there. Right. The UK has had several days now where it's been very close to running entirely on renewables. And it's still a few years away before we can make that a kind of permanent thing, but we are getting there. Right, there are some sectors where it's difficult, but we know ultimately how to avoid dangerous climate change, and that's net zero. Right? If you stop emitting CO2, the Earth stops warming up. The problem with SRM is it doesn't really deal with that. Right? It's some other kind of thing that says, well, maybe you don't need to actually deal with the problem. You can kind of hide it somewhere, and maybe the negative impacts fall on someone else. And yeah, I find that concerning.
That was actually, I should interrupt and just say, please, all of the listeners, please feel able to ask your own questions. I'm going to open this up for you to ask questions very soon, but write your questions into the chat box, which you'll find at the bottom of the Zoom screen. and please don't be shy. Um, I'm going to ask some really dumb questions to make you all feel better about the clever ones you can come up with. Um, in a way, you raised something quite threatening then, Ed, and it had been occurring to me. Um, if you can control the formation of clouds, you presumably can impact the places where precipitation takes place, that is, rain and water. And if you've ever met a farmer, they're extremely interested in um, getting the rain and water at the right time for their crops and not getting too much. But the idea of control of the formation of clouds is very appealing. And indeed, I can speak from experience. I know in certain countries, they've tried cloud seeding. It's a very common thing that people have tried in the United States and in Canada, for example, and indeed in Russia, where they have vast areas where they're trying to grow food crops like which require water at a critical time in the food in the growth of the plant. What's the problem then is it does take it onto a sort of geopolitical level. Do you want to comment on that and indeed on the idea of helping the farmers?
So I guess ultimately, maybe I suggested kind of too much potential control here, in the sense that you can't make a cloud out of nothing, right? Like these are kind of relatively small changes in existing clouds, right? So with cloud seeding for rain, you're finding clouds that were on the edge of raining anyway, just trying to kind of push them over the edge and make them rain. Here, you're making relatively small changes to clouds across the globe, which ultimately then kind of feeds back to global temperature. But both of these things actually have a similar problem, which is how do you tell whether you did anything at all? Right. So for cloud seeding, you're trying to find clouds that were about to rain or were going to rain and just give them a little push. But obviously, if you're looking for clouds that were going to rain or close to raining, maybe if you just waited a bit, they would have rained anyway. Right. And the issue, one of the big issues with SRM or solar radiate like geoengineering is imagine you tried cooling the climate, right? You've done something and that tried cooling the climate, and then the year afterwards, there was a big drought in Africa. Was that your fault? Would that have happened anyway? Should you stop? Maybe it was unrelated. Um, and those kind of attribution questions become really difficult. Like how do you decide whether to stop your program or not? How do you avoid making the wrong decision there as well? Um, and I think those kind of questions are going to be really, really tricky if we start going down this path. Like how do you decide whether to continue doing this or not? Who's in control? You notice on these maps that the reduction in rainfall is different in different regions. Some people might want more geoengineering, and some countries might want more geoengineering, whereas others want less. Who decides? I don't have a good answer for that.
I'm not sure whether you answered my question, but it certainly made me even more nervous about the future. Um, I really would like to um, move to some of our members asking questions. And I see first question that came in is from Max Whitby. Would you like to pose your question, Max? Unmute yourself and
Sure. Can you
pose.
hear me clearly?
Yes, brilliantly. Go ahead with
Good.
your
Well,
question,
what a
please.
fantastic talk. Such interesting work and brilliantly presented. I used to be a member of the Cloud Appreciation Society, but I then took up astronomy and had to resign. My question is about forecasting. One would think possibly that quantum computing, if it ever works, could be relevant in the sense that it can explore huge numbers of permutations in a way that's not possible by scaling conventional computing. And then, of course, there's AI, and one's heard a bit about how AI is impacting weather forecasting. Since you're deeply embedded in this world, could you give us your assessment?
Yeah, so I mean, weather forecasting in particular is almost like the perfect problem for AI, right? Like you've got huge amounts of data, and you can relatively quickly verify almost whether or not your AI is doing something, is doing a good job or not, right? You get it to make a forecast, and then in 2 days, you know whether it got it correct or not. It's a little bit harder for the climate because obviously we want to make a forecast of something that isn't in our training data set, right? We haven't seen it before. And so it's also then kind of difficult to verify whether we got it correct. Um, but there is absolutely a role for AI here. Again, we have huge amounts of data, and using that to construct kind of models that can better represent the Earth, and so tell us how the Earth is changing, is absolutely going to be kind of a central part of like weather and climate going forward. Um, as for quantum computing, um, actually, one of the areas that's kind of been of interest in a fairly kind of recent past is stochastic computing instead. That there's a lot of parts of the kind of weather that require a bit of randomness, right? So I remember I said we were kind of chopping the Earth up into chunks. A weather forecast can chop things up into smaller chunks, but they're still relatively large. They might be 1 to 10 kilometers across. And so you've got your equation that describes clouds in there, but there's some uncertainty or kind of on what that kind of how correct that equation was. There's some extra randomness. And so one of the ways that some weather centers have kind of improved their models is to add that randomness back in, right? Say, well, this is what I think the clouds can do, plus an extra random bit for things that I didn't properly include in my equation. And it turns out that if that's what you want to do, you can change the architecture of your computer to do that faster. So rather than solving everything and then adding randomness, you just get a computer that's a bit worse at doing maths, right? Like it doesn't do everything to kind of a super high precision. It drops a whole load of decimal places, and that adds in the randomness in a much faster way. And so there are kind of various ideas that you could get computers that are kind of specially designed for this, that are in some ways just worse at doing maths, but better at doing the kind of weather forecast kind of maths. So it's not directly about quantum computers, but a different kind of computer that I think is still interesting here.
Thanks.
Can I just add a couple of thoughts on that? Because I was at an event at Imperial a couple of weeks ago. It was the Center for one of the conversion science, and they had a AI Collider event. And there were really good presentations around kind of how the intersection between AI and some of the fluid dynamics modeling was being done. Kind of a new area called neural physics, which I hadn't really come across. So is that an area that would impact? I think a lady called Claire Heaney presented on some of the work that they're doing on modeling emissions in kind of urban environments.
Yeah, I'm not familiar with her work directly, but absolutely, these are kind of I guess like a class of ways of replacing different parts of your model with kind of machine learned or versions, right? So there are different ways you can do this. Some of the kind of AI weather models just take input data and convert it to weather forecast. They might calculate some stuff kind of internally, but what they're doing is they're saying this is the best data I have, and this is what my weather forecast is. In other cases, you might just use the AI to replace different parts of the forecast, right? So you might have what we refer to as the dynamical core, which kind of solves the large-scale fluid dynamics across the globe. And you might say, well, we understand the maths of that pretty well, and we could use AI to do it, but maybe that's just something where we say, we're just going to solve the maths because we're good at that. But the clouds, for example, we're going to have AI represent the cloud part of it. So instead of working out our equation for clouds and then implementing that in every location across the globe, we use some data maybe from a very high resolution model that runs on a limited area. And we use that to kind of machine learn the equation for clouds. And so you can replace different parts of it, of your kind of weather model or your climate model, in different places with these AI components. And I think that's, again, like a really kind of exciting way forward. Like if we know the physics for some part of it, but the other parts of it where we're less clear but have a lot of data, maybe those are the bits we can target to specifically improve.
Yeah, we're just about to set up our program for next year, so that's an area which I think will be we'll get a specialist talk on. David, shall I take over the Q&A so you can
If you wish, yeah.
yeah, if you can relax for the next 10 minutes. Katri and Derek, which one of you, I don't know, but you had a question on contrails, and I know Ed had some thoughts on contrails we touched on earlier. Do you want to come on camera to ask the question, or should we just take it?
Yeah, we can come on camera, but you seem to have it set that we can't do it somehow.
Oh, you should be able to.
It says you cannot
Well,
start the video because it's disabled by the host.
Okay, well, you could talk
There you go.
because we can hear you.
Yes,
There
I
you
actually have two questions. So the first one is on the chat. Do airline contrails work in the same way as ship tracks?
Yeah. Okay. Do you want to do them both now, or shall I do one then the
Okay,
other?
so that's the first question. The second
Yep.
question is actually to do with the graph that you have on the screen at the moment.
Yep.
And I just wonder if you could clarify exactly in that model. I think you said they were relatively simple models. Why are you getting such a strong temperature rise when there's a strong cooling effect? What's going on in the model to do that?
Yeah. So I'll start with the second one first because it's on the screen. So ultimately, what's going on here is that you have the kind of cooling effect from aerosols being offset by some warming effect from greenhouse gases. And the key kind of constraint here is that these two models have to kind of get the 20th century temperature change about correct, right? So we kind of know what the kind of change in temperature was in this case in about kind of the year 2000, 2005 or so, versus pre-industrial. So if you have no aerosol cooling, you have to have a much weaker warming from greenhouse gases. Otherwise, your temperature in 2000 would be too high. If you have a very strong aerosol cooling effect, that then means that your Earth also has to be very sensitive to greenhouse gases, right? And so as you go into the future, we expect our aerosol cooling effect to decrease, right? So governments tend to want to decrease aerosol emissions because these particulates are harmful for human health. And so as that decreases, you'll kind of unmask this much stronger warming effect going into the future. So if you have a strong aerosol cooling in the past, you also would have had an Earth that was very sensitive to greenhouse gases. And so it's having a strong kind of masking effect. And so as you head into the future, you then unmask that very high warming. That makes sense.
That does, yeah.
So the contrails are interesting because they are a bit different. In some ways, they're similar, right? They're formed by transport and aviation. Let's see if we can get back to this part here. Ship tracks form in very low clouds, right? Because the ships obviously are on the surface. That aerosol doesn't get very high up. And so they make low clouds brighter. Now, if you look in this image here, these clouds off the coast of Africa, can you see the mouse? Hope
Yes.
so. Yeah. So these clouds off the coast of Africa are very bright. So you see they're reflecting lots of light. They're white, not quite red, but fairly close. But if you look at them in long wave, there's not really much contrast with the ocean next to them, right? Because they're low, they're basically the same temperature. And so they don't really change how much energy the Earth emits. These blue clouds here are much higher, and so they're colder, and so you get a very high contrast with the Earth below. So if you have a warm Earth surface and you kind of cover it up with a cold cloud, it means the Earth emits a lot less energy to space. And that's kind of what a contrail does, right? So contrails are very high and cold, and so they're much more like these blue clouds here, in that they cover up a nice warm Earth surface and they trap energy in the Earth system. They also do a bit of reflecting because they are white, but on average, we think contrails warm the Earth. So in particular, any contrail that forms at night only has this infrared warming effect. Like there's no sunlight to reflect. And so one of the things you can do to reduce the climate impact of your flying is to fly during daytime. Sounds fairly straightforward, but nighttime flights, particularly if they're producing contrails, have a significantly larger warming effect than daytime ones do.
Thank you.
Yes.
Okay, thanks for that. Jana Tama, you've also got a question?
Yes, I couldn't help noticing when you showed the ship's trails how different they were. And I was wondering if they are kind of especially bad ships, or is everything related to the conditions, meteorological conditions that determine it?
So there are a couple of things that are related. So part of it is the kind of cloud. So some clouds are just more sensitive to aerosol than others, or more sensitive to ships. Part of it is the background aerosol environment. So if it's already very clean, adding a bit of aerosol from a ship will have a much larger effect than if you're adding it into an already polluted environment. But part of it actually is the different ships have different effects as well. So we see the kind of change in fuel and the difference in ship fuel having an effect. We can see differences between different types of ships as well. So actually there were studies done back in the 90s, mostly by people like the US Navy looking at this, because they'd seen these trails in satellite images and wanted to understand them. And you see, for example, nuclear powered ships don't generate these trails, right? And actually ships running on LPG, like liquefied gas, typically don't generate these trails either. It's coming from the sulfur in the fuels. So yeah, different types of ships do definitely have different effects here on the cloud. It's not just the cloud types themselves, although that is really important.
I guess as an extension to that, one of the drivers for low sulfur fuels is, I guess, the aerosol goes up, it rains, yeah, the sulfurous compounds come back down into the oceans, which acidify the oceans. So like your model of, okay, let's burn a bit more sulfur. Well, actually, the oceans would get more acidic.
I want to say right now that I'm not a proponent of that, right? But yes, I mean, air pollution in particular, actually, for ships is quite important. So the Dutch, for a long time, have been concerned about this because if you think about ships polluting in the English Channel, the wind there typically blows from west to east, which means that all of the pollution that gets generated by ships in the English Channel gets blown over the Netherlands. Like we get some of that here in the UK as well, but it's much less severe. And so that's part of the reason for those coastal emission control areas. But even stuff that's emitted out over the ocean, some of it makes its way back to land as well.
Okay. Well, thank you. I think we've covered the questions, David. So if you're...
Thank you, Bill. I was just going to intervene. We're at the witching hour when really it's my duty to say thank you to you, Ed, for, I think, a very stimulating discussion of clouds. I think really one can't look at a cloud now without thinking, where did it come from, what's it carrying, and where's it going, and what it's doing for us. They're clearly a critical element in how our planet evolves, and clearly it's sensible for us to find out how the cloud systems work. I think you've explained it really very effectively, and I think probably the best thing I can do is simply ask all of the listeners to express their appreciation either by unmuting and making a noise like this, or using the clapping form, which I think you can see. Really, a truly excellent performance, Ed. Much appreciated by friends of Imperial College. Thank you. And I have a feeling we might be coming back for advice on next year on other things we might look at. Thank you very much indeed.
Thank you.
Thank you, David.